Welcome to part B of chapter 8. In part B, we will go over section 8.5, 8.6, 8.7, and 8.8. In 8.5, we will look at the drawing the Lewis structures of molecules and polyatomic ions. So far, in the previous section, part A, we learned how to, or we looked at how to draw the dot symbol for main group elements. On my whiteboard, there is group 1A through 8A, just a few elements representing each group. For all group 1A, what we know so far is that they have one dot next to the chemical symbol. This is the Lewis dot symbol for main group elements. Group 2A, they have two dots. Group 3A, 4A, 5A, 6A, all the way to 8A. That's what you should know in order to grasp and understand drawing Lewis structures for molecules or polyatomic ions. There are rules which you need to commit to your memory. It will be handy when it comes to drawing the Lewis structures. It's the same, individual who proposed that when elements react, atoms of element, when they react, they use their valence electrons. The rules we will go through is rule number 1. I'm just going to synthesize 8.5. I'm going to synthesize rules you will use in drawing the Lewis structure. Let's say drawing, I'm just gonna title this drawing Lewis structures for molecules or ions. Let's just put just ions here. Rule number 1 is you should be able to calculate the total number of valence electron in the molecule using phosphorus trichloride. Phosphorus trichloride, and as an example, here is one count or determine the total number of valence electrons. Let me just use this for electron in the polyatomic ion, all right, in polyatomic ion or molecule. It's not always that you will be working with neutral molecules. Sometimes you may be given polyatomic ion. And the way you do is the 35 you see here is we have phosphorus, which is what? In group 5A. So this is 5 times 1 electron, or rather here it is 5 electrons. It's in group 5A times 1. We have 1 phosphorus, therefore 5 electrons. Chlorine, right, is in group 7A, 7 valence electron times 3. We have 3 chlorines, therefore you see these 3 because of 3 chlorine, 7 for 7 valence electron. This is in group 7A, which means 7 valence electrons, and this is in 5A, which means 5 valence electron. which gives us 21 electron. If we add, this will give us 26, all right, 26 valence, 26 valence electron. So these 26 you see here is the total of number of valence electron in phosphorus trichloride. Take note of this, take note of the 2 bullet points here. For anion, that means negatively charged. For cation, that means positively charged. Here, you add or subtract. I'm going to demonstrate using carbonate, for example. If we have carbonate, this is a polyatomic ion. It's a polyatomic ion. And how will you move forward with that? I'm going to illustrate the addition of extra electron. Carbon is in group 4A, times 1. Therefore, we have 4 valence electrons, 4 valence electrons. Oxygen, we have 3 times 6. It's in group 6A. This will give us 18 valence electron. If you add up that, adding that, this will give us 22 valence electron. If you have an overall charge, look here. If you have an overall charge of a negative, you add extra 1 electron. Since we have 2 electrons here, we will have to add here these 2 here. You see plus 2 extra. All right, 2 extra electrons, and here's 24 valence 24 valence electron. This is what you do for polyatomic or just anion negatively charged particle. If you are dealing with cation such as ammonia, NH4 positive, this is ammonium. In this case, we will subtract. So this is how you proceed with this. Nitrogen is in group 5A, 5 electron times 1 equals to 5 electrons. And then hydrogen is in 1 electron times 4. This will give us 4 electrons. If we add this will be 9 electrons. The overall charge you see here, the overall charge of positive 1 will have to subtract 1 electron if a cation. Therefore, this is a cation. This is cation. Means it's positively charged, we will subtract, all right? You say minus 1 electron. If it is plus 2, and then you subtract it. So this is 8 valence electrons, 8 valence electron to work with. So rule number 1 in drawing Lewis or writing Lewis structures for molecule is counting the total number of valence electron. And for most part, you will be dealing with main group elements, or with the group number. The group number tells you the total valence electron for that atom. Now, so far, so good. Let's see, rule number 2 here is drawing the skeleton, all right? Rule number 2, draw the skeleton of the molecule with less electronegative element at the center. In other words, the less electronegative. We looked at electronegativity in the previous section, and you should know the trend, okay? So the less electronegative is always the first element in the chemical formula. For example, phosphorus in the previous section, phosphorus is less electronegative, chlorine is more electronegative. Therefore, it will be our central. Phosphorus is our central. And what you do is just draw the skeleton of the molecule with the phosphorus at the center, hooked up to the chlorines. So you should be well-rounded in identifying the central atom. Not always that you'll have the central atom. Sometimes you may have only two elements. It's just gonna be linear, such as O2, oxygen. It's just gonna be OO, and we don't have a central atom. Or you may have Cl2 for chlorine. You don't have the central atom. But for this case, you will have phosphorus, which is less electronegative at the center. We call it central atom. This is here. This is central atom. We will need this in chapter 9 to identify the central atom. We call this, or let me label this as external atom. All right, so once you identify, or once you come up with your skeleton of the molecule, rule number 3 here, 3 is subtract bonding electrons from the total number of valence electrons, total number of valence electrons and distribute the remaining on the external atoms such that octet rule is obeyed except hydrogen. So that's what you need to remember for rule number 3, is subtracting the bonding electron. Here we have 2 electrons. If I do have this, we have 2 electrons here, we have 2 electrons here, we have 2 electrons. We call this bonding electron. We'll need to subtract that so that whatever is left over, okay, we give it to the external atom, say that the octet rule. Let's see. We had 26. This is valence electrons minus 6. These are bonding electrons. These will give us 26 electrons remaining. 26 electrons remaining. So that's how you keep track of how many electrons are left, is by subtracting 6. The 6 here is from the bonding electrons. There's a bond here for 2 electrons. There's a bond here, 2 electrons. 2 electrons will remain. So based on this rule, the external atom, in this case, each chlorine should end up with A2 achieve or fulfill the octet rule. So in this case, it's going to be P. So if I hook up this chlorine, 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 we have two dots. So we have given each chlorine 6 more to make it 8. The octet rule, we have 2 electrons, 2 electrons, 2 electrons, 2 electrons. So whatever it was left, 20 minus 1, 2, 3, 4, 5, 6, 7, 8, 9 minus 18 electrons. This will give us with 2 electrons. Whatever is left, just put it in the central atom. Don't worry about it. Just put it anywhere in the central atom. In this case, the left over here, just come to, or maybe we'll have used this, 2 electrons. We just keep it to right here. That is where we have the 2 electrons. You can use to convert the lines to dots, all right? You can use to convert the lines here, that's the bonds, the single bonds, into dots to make a dot structure. Look at how the octet rule has been obtained by each chlorine, and this leads to this structure. Nothing remain. We don't need to make any multiple bonds such as double bond or triple bond. We'll see later on how to generate a double bond or triple bond. If there is nothing left, make sure that, all right, make sure that each atom fulfill or satisfy the octet rule. And the way it is, there's nothing left. Each atom in this molecule satisfy the octet rule, and this is the Lewis structure. Now, if in the event that an atom does not satisfy the octet rule, you can bring the electron from the external atom to make a double bond or triple bond. Here is a good example of generating the octet rule. Please do not, all right, do not just add electron to satisfy the octet rule, all right? If we end up with this, how we ended up with this is, if I start off with the first one, HCN like that, hydrogen cyanide, carbon is 4 times 1, we have 4 electrons. Hydrogen is 1 times 1 equals to 1. Nitrogen equals to 1 times 5. We have 5 valence electrons. If we add up, we have 10 valence electron. 10 valence electron. Just this is rule number 1. Rule number 2 is to draw the skeleton. So if I have carbon bonded to hydrogen and nitrogen, subtract the bonding, minus 2 plus 2, this is 4. We remain with 6 valence electrons. So if I look at hydrogen does not need more than 2 electrons. There was an exception. Hydrogen only need 2, and the way it is, it's such. So between carbon and nitrogen, the external atom takes first priority in getting or satisfying the octet rule, minus 6, we remain with just 0. So as it stands, we have now this structure C, N, but if you look at carbon, it has 6 electrons instead of 8 to satisfy the octet rule. So what this means is if we make this bond here, 1, 2, if we take this, this is the structure. Nitrogen satisfied the rule, but carbon has 6 instead of 8, 6 instead of 8. So we still need to use this to make a double bond, triple bond. So triple bond, and this is the structure for hydrogen cyanide. So the double bond or triple bond has to do with satisfying the octet rule. If the external atom satisfies the octet rule, the central atom does not end up with 8 electrons. Please use the lone pairs. We're going to talk about the lone pairs, the unshared electrons to make a double bond or triple bond, to make a double bond or triple bond. Here is a question on Lewis's structure, right? The ion that is Cl negative 4 has how many valence electron? This is simple. This is given the periodic table. Iodine is in group 7. Electrons times 1 equals to 7. Carbon, chlorine is in 7 times 4. If I add this, will be 28, 35, and then there is an overall charge there of 1. We have to add 1 electron, and we have 36 valence electrons. 36 valence electrons. So this is just a question of using the periodic table, looking at the polyatomic ion, the overall charge. There is an overall charge of -1. That's why I added 1 here. This is for extra. I would like to bring to your attention that, please, you should be able to write down the chemical formula for polyatomic ions, such as sulfide. Do you know the chemical formula for sulfide, for phosphide, for phosphate? All right, for carbonate, and so forth, so that when you are asked to find the total valence electron, you just have to add up. Otherwise, when you are given the chemical formula, it's much easier. It's much easier. Now, that is all what I wanted to bring to your attention on Lewis, drawing the Lewis structure. Please make sure you practice end of chapter problems. You should have problems on drawing the Lewis structure. Now, at times you may end up with possible more than one structure for the same molecule. What do I mean by that? You can have 2 structures, you can have 3 structures of the same molecule, yet it is satisfied the octet rule. Each element in the molecule satisfy the octet rule, or polyatomic ion satisfy the octet rule. How will you determine which one is correct or which one is more plausible Lewis structure? It has to do with, or you need to use, you'll use the formal charges. You will assign formal charges in the compound or in the molecule, so that you see the possible structure with the least combination of what? Formal charges, that is the plausible Lewis structure for that molecule. In other words, the one with the least Lewis, the one with the least formal charge, sorry, is the plausible Lewis structure for that molecule. And Lewis's formal charges has nothing to do with the group number. No, you cannot use the periodic table to predict the Lewis structure, but you have to use this equation. Formal charge is given by valence electron. Let me just electrons minus non minus a half bonding electrons. So the equation is right here. Formal charge is valence electron for the single atom minus half the bonding. A good example here is carbon dioxide. If we are to assign the, all right, if we are to assign the formal charge to each element in carbon dioxide, we will look at the first oxygen carbon at the center, and then the second oxygen. Using the equation, all right, using the equation given in the PowerPoint slide here, valence electron. The first hydrogen, the first oxygen here, valence electron is in group 6. Therefore, we have 6. This is in group 4. This is in group 6. So if I want to assign this number so that you see, I can just have this structure here. And let's say number this is 1 to here. Formal charge for oxygen number 1, for example. Valence electron formal charge is, valence electron is 6, is in group 6A. That's where it's coming from. If it was a different element, then in this case going to be main group, just use the periodic table minus, I don't see, or there is here, sorry, there is 4 electrons, 1, 2, 3, 4. So minus 4, you see this non-bonding. I'm using my equation here, non-bonding, these are non-bonding electrons. These are here non-bonding electrons. We have 4 in the first oxygen, 1, 2, 3, 4, minus a half bonding electrons. Bonding electrons, we have 1, 2, so 4 times 4 here, this is 2. This will give us 6 minus 6, which is equals to 0. It has a formal charge of 0. That's why we have it here, formal charge. The other uses a different approach, but it's just gonna work the same way. If you say valence electron minus non-bonding electron on that atom minus a half bonding. Half bonding here is there are 2 electrons in each line. So here we have 2 electrons, and then here we have 2 electrons. Therefore, the 4 is coming right there. If for carbon, formal charge for carbon, valence electron is 4 minus minus 0. I don't see any non-bonding minus a half. If I look at carbon, there is, look at carbon, there are 2 lines here, there are 2 lines here. So 8 bonding electron. So 4 minus 4 equals to 0. So carbon has a charge of 0. It's the same thing for the second one. If you have a triple bond on one side, these are the formal charges which I don't want to go through using the same equation, but from the formal charges, this one has the least combination, this one create a combination in terms of formal charges, and this is the most plausible, the one with the least combination for formal charges is the possible, the Lewis structure for that compound using the Lewis using the formal charge to decide. So please remember when we have different structures, we can use formal charge to decide which one is the most plausible. Here is another example. If you look at these structures, these are just structures of the same compound, but having different position for either double bond or triple bond, and all of them, each element satisfied the octet rule, but the one with the least, the one with the least combination of formal charges is the plausible Lewis structure. If in the event that 2 molecules or 2 structures have same combination, as in this case, all right, this is -1, this is -1, this is -2, it's not going to work this way. But for this, how do you know which one is which? The structure whose Lewis or less, the structure whose formal charge reside on less electronegative or more electronegative, sorry, is the most plausible. For example, here, if I look at the position of nitrogen, it is more electronegative. So we'll have this structure. This is more electronegative compared to sulfur, even though we have negative here. Based on the rule what I just said, the structure with a formal charge of negative being more electronegative is the most plausible one, most plausible. You see this formal charge closest to 0 can be written as that. Let's see on formal charge, this is simple. What is the formal charge on nitrogen in nitrate ion? Valence electrons minus non-bonding minus a half bonding electrons. So in this case, we have 5 valence electrons. It's in group 5 minus 0. I don't see any non-bonding electron on nitrogen, therefore 0. Minus a half, I see that we have 1, 2, 3, 4. There are 4, 1, see this 1, 2, 3, 4 times 8. Remember, one line has 2 electrons, so it's gonna be 5, 4 equals to +1. So nitrogen has a formal charge of -1. If you are given the chemical formula, all right, or even the structure like this, it will be very easy for you because to see the what? To see the non-bonding electron, to see where bonding electrons are. But if you are just given the chemical formula, you need to draw the Lewis structure and before you calculate the formal charge, and the correct answer for that is C. All right, the formal charge for that. So, well, I just explained the formal charge. Why do we need to determine the formal charge? It is used to determine which structure among the possible structure for a molecule, determine which one is the most plausible, most acceptable. If you have more than one possible structure, octet rule being fulfilled, those structures we call resonance structures, and that is what we are going to look at in 8.6. Remember, formal charge is used to determine which Lewis structure is acceptable among 5, 2, or 3 possible structure of the same molecule. We call those Lewis structure. Here is an example of ozone, all right? Ozone has a chemical formula O3, and it can have O, or all right? The double bond can change. We call these resonance structures, Formal charge is used to determine which one is plausible, all right? Here is a nitrate. We use the double-headed arrow to indicate resonance structures. This has 3 possible resonance structures for carbonate ion. And if you take note of these structures, they only differ by the position of the double bond just around. If you look at the first ones, oxygen at the top, on the side. Likewise for carbonate ion, the position of the double bond. We call this Lewis structure. We call those Lewis structure. Call it Lewis structure. Okay. Now, how many equivalent resonance structures can be drawn for SO2 without expanding onto sulfur? For this, you need to draw the Lewis structure, which means sulfur equals to, in group 6 valence electron. Oxygen is group 6 times 2 is 12. So we have 18 valence electron for that. We'll have to write this skeleton, which means sulfur is bonded to 2 oxygen. Recall rule number 2, or rather 3, subtract the bonding electrons, and whatever is left over, external atom take first priority in satisfying the octet rule. So if we know that we have 18 minus 4 remain what? Remain 14. All right, so let's give each extra electron to each external atom. We have used 12. So there are 2 electrons left. Please do not create extra electrons on sulfur to satisfy the octet rule. But you can either use this and get rid of that. Or rather, we're gonna make this double bond here. Rather, so that sulfur and oxygen, they satisfy the octet rule 8. 1, 2, 3, 4, 8 on oxygen. 1, 2, 3, 4. It satisfies the octet rule. Even the last oxygen, 1, 2, 3, 4, which can also be O, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, and then double bond on this side. And we have only two possible, so the correct answer here is B. There are two possible structures. So unless you draw the Lewis structure, move around the double bond, you won't be able to determine the possible resonance structure. And remember what I say, resonance structures are structures of the same molecule. The only difference is the position of either the double bond or triple bond. Double bond or triple bond. That's all for 8.6. Now, home stretch 8.7 exception for octet rule. There are three cases, all right? There are three scenarios where the octet rule is exceptional. One, if ion, remember ion is a charged particle or molecule with odd number of electrons. So in some cases, you may be given a chemical formula for a compound, but when you try to satisfy the rule, no matter what, you still end up with less than the octet. That means each atom does not end up with 8, and we'll see that in a moment. Now, other exception is when a molecule, all right, when a molecule with less than octet, that means we don't have enough electron. And lastly, ion or molecule with more than 8 valence electron, expanded octet. This, you'll see this when dealing with transition metals, because transition metals, they are in the D block, and D sublevel can take a maximum of 10 electrons. Therefore, we say expanded. So here is scenario one. We have odd number of electron, nitrogen monoxide. All right. So no matter how we try, we have a less number of electron. Therefore, we don't end up with 8. And you cannot just add electron to make it what? To make it 8. Or if we have fewer than 8, the element in second group, for example, boron, you see boron has less than unsatisfied the octet. These are just less important. So if you look at boron 1, 2, 3, it has 8. It has 6 electrons. It's stable that way. So with fewer than 8 valence electrons, still possible to have Lewis structure. This is an exception. Boron, remember, boron, beryllium, those are exceptions. They do not end up with 8 when they form compound. So the possible structure for boron trifluoride, each element in the molecule satisfies the octet rule, including boron, with only 3 lines instead of 4 to satisfy the rule. Now, exception of octet rule, last exception is when you have more than an octet of valence electron. In this case, row 3 and below, they have this sublevel. We can take up to 10 electrons. Therefore, it will form, or it can accommodate more. We say those are hypervalent molecules. All right, hypervalent molecules. So read those 3 exceptions. Be wary for that. Of the following dash cannot accommodate more than one. So the only exception for this list is beryllium. The rest are in the D block, which means they have a sublevel which can take more than what? More than 8. So it's a question of understanding the periodic table. Lastly, let's look at the strength of covalent bonds. This is something we looked earlier on, and remember when we talk about the lattice energy earlier on, it's the energy required to completely dissociate 1 mole of a compound into gaseous state. And remember the trend on ionization energy in relation to atomic radius. The smaller the radius, the harder it is because of strong electrostatic. So point enthalpies are positive because we are adding energy to break them apart, which makes sense. These are just few. I don't want you to memorize table 8.3, but there is a pattern here. If you look at all these carbon, I'll say carbon hydrogen, it is on the extreme end. Fluorine, Y413. If you look at carbon fluorine, 485, this has to do with the electrons and the ionic radius. This is short. This is long, but more electronegative. More electronegative, therefore it will be hard to remove. The double bond, all right, average bond enthalpies. Double bond is always stronger. These are just single bonds. Double bond is always stronger than the single bond, and stand out the strongest among the single double bond is the triple bond. Look at the trend, nitrogen, 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 nitrogen. There is an increase in bond envelope, bond envelope. So you should be able also to look at the trend with the atomic radius. Let's say if I'm going down, the radius keeps getting big. For example, here, I can say this is hydrogen is constant, or rather, I may want to say this. If you look at the fluorine, it is getting larger and larger and larger, and therefore it will be easier to break. Remember, bond envelope has to do with breaking of this bond. And the larger the radius, especially for the anion, the radius, ionic radius is getting big and big and big. And then it's very easy to split that. It's very easy to split that. Well, here is an example on interactive problem. That means you will have to critically think before you arrive at the answer. I'm not going to go through the determination of the molecular formula, but we wanted to, or just dive to the Lewis structure for this molecule. This is just walking you through determination of the structure. Here is what I want us to look at in determining the bond envelope, that we got to break the carbon chlorine, carbon double bond oxygen, carbon chlorine atom, all right, in order to determine the bond envelopes. So here, I see this is the plausible structure. This is not because of positive one, negative one, so applies the same thing there. So what you need to look at is the bonds being broken. Double bond, single bond, single bond. Double bond, single bond, single bond. And then you add up to that. So if the reaction here, this is where the reaction in the formation of benzene. Carbon monoxide reacting with chlorine gas. Remember, calculate its product, no, reactant minus the product. This is the product, this is the reagent. Therefore, the bond dissociation here is the product minus the reagent And this is the reaction is exothermic giving away heat. Please follow that to see how that is completed. Let's see, using the Pond dissociation energies, the envelope for reaction for the following is, so if I want to do that, please try on your own. If I look at, we are breaking here, carbon double bond. So it is carbon is 1 times right here, 614 plus carbon here, 1, 2, 3, 4, 1, 2, 3, 4, 4 times carbon to hydrogen is right here, 413, plus hydrogen chlorine is right here, 431. Okay, these are the product, minus the reagent here, carbon is 348. I'm looking at this carbon plus carbon hydrogen is 1, 2, 3, 4, 5. So 5 times carbon hydrogen is 413 plus carbon chlorine right here. Carbon chlorine is 328, 328. You need to do the mass, add this, and subtract. Remember, reactant minus product to get the bond enthalpy. Reactant minus the product. This is just bond enthalpy and the bond length. The triple bond is shorter than the double bond, which is shorter than the single bond, which is shorter than single bond. This slide here, you may be given a series of compound and you are asked to arrange them according to increase in bond enthalpy or decrease in bond enthalpy, or identifying the one with the greatest bond enthalpy. It has to do with the double bond, the double bond. Our learning check, which bond has the highest bond dissociation energy? Based on the previous slide, of course, TCC, okay, the strongest. It's just like having 3 toothpicks versus only 1 toothpick. Which one is easier to break? Common sense. 1 toothpick is easier to break than 3 toothpicks or even more, okay, or even more. So please read more on the bond length and bond strength in section 8.5. And generally, I'll recommend that you complete my lab and mastering assignment before attempting the quiz, which I will post momentarily. Thank you.